Welcome to the IECC Inspection Guide series, the first in a series of short inspection lessons based on energy efficiency measures developed by the Department of Energy's Building America program and brought to you by BARA, the Building America Research Alliance team. In this lesson, we'll explore buried and encapsulated ducts. In this short 5-minute lesson, we'll explain what buried and encapsulated ducts are. We'll touch on duct thermal losses and how to mitigate them. Then we'll examine ways to bury and encapsulate ducts using closed-cell spray foam, fiberglass bats, and blown-in fiberglass. Finally, we'll look at beds through the lens of the Building and Energy Code and end with an inspector's checklist. Buried and/or encapsulated ducts, also known as beds, are an energy efficiency strategy to reduce ductwork thermal losses in unconditioned attics. Beds are simply ducts covered in loose-fill insulation and/or encapsulated in closed-cell polyurethane spray foam insulation. As building codes raise requirements for duct sealing and insulation, and as the building industry has struggled to address ductwork thermal losses in new and existing homes, beds offer a flexible approach to reach energy efficiency goals. While ductwork installed within the thermal envelope is one solution, beds can approach or even exceed the performance of ductwork placed within the thermal envelope. Studies by the Department of Energy's Building America program have determined that ductwork installed in unconditioned spaces, such as attics, crawl spaces, and garages, can contribute significantly to the overall heating and cooling costs of residential buildings. Estimated duct thermal losses for single-family residential buildings with ductwork installed in unconditioned spaces range from 10% to 45% of a building's total cooling and heating loads. Forced air heating and cooling systems distribute air via an air handler and a duct system. The air handler is designed to remove air from the house, heat or cool it, and supply it back to each room. Duct leakage can occur on either the supply side or the return side of the air handler, as well as in the air handler itself. Both supply and return leaks cause the air to move in unplanned, unpredictable ways, usually through the unconditioned spaces and often bypassing air, thermal, and moisture barriers, as well as air filtration systems. Those leaks can account for almost half of the total heating and cooling costs of some residential buildings. Energy losses from duct leakage to the outside, which, as we've seen, can be as high as 20%, are exacerbated by large temperature differentials between the conditioned air inside the duct and the air in the unconditioned attic. During the cooling season, 55-degree Fahrenheit conditioned supply air can be separated from hot 120-degree Fahrenheit ambient attic air by duct insulation as low as R4.2. During the heating season, this temperature differential can be even higher, with 110-degree Fahrenheit supply air passing through cold attics with 20-degree Fahrenheit ambient temperatures. There are 3 primary methods of reducing ductwork thermal losses in unconditioned spaces. They each have various cost, performance, safety, and practical trade-offs, but properly implemented, each can greatly improve heating and cooling system efficiencies. First, properly installed ductwork, well sealed and insulated to current IECC code, can drive ductwork thermal losses down to around 10%, but further reduction requires more advanced techniques. As a second approach, by installing or moving ducts within the thermal envelope, duct thermal losses can be eliminated entirely. However, depending on the method employed, living space may be affected. Finally, by burying and/or encapsulating ductwork in attics, the beds approach, ductwork thermal losses can be reduced to around 3% or less. This course is focused on beds, but for background, here's a slide that shows 4 ways creative home designers are beginning to bring HVAC ducting into a building's conditioned space. Figure 1 shows ducts in an insulated, unvented attic. Figure 2 illustrates ducts installed in a dropped ceiling. Figure 3 shows ducts in a space created by a modified truss. And Figure 4 shows ducts running between floors. In all 4 cases, ducts are inside the building's thermal envelope, so even though there is a slight leakage, the heat or cooling remains in the conditioned space. Buried and encapsulated ducts will reduce the heating and cooling loads of the building, and as a result, the space conditioning systems may be downsized in some cases. In new construction, equipment downsizing will reduce the cost of implementing a bed strategy. In retrofit scenarios, the energy savings and costs of a bed strategy will depend on whether a new, downsized space conditioning system is installed. If the space conditioning system is not downsized, the reduction in load associated with beds may increase cycling in the space conditioning equipment, reducing the efficiency of the equipment and energy savings. On the other hand, simultaneous replacement of space conditioning equipment and implementation of a bed's strategy may be a way to reduce installation costs and maximize energy savings. There are 3 possible duct insulation strategies: buried ducts, encapsulated ducts with closed cell spray foam, and the combination of buried and encapsulated ducts. The best solution depends on the climate, age of the house, and the configuration of the HVAC system and attic. Ducts that are only encapsulated without burial are not recommended for new construction simply because additional burial requires only minor increases in planning and costs over encapsulation alone, yet yields significantly higher performance with minimal additional effort. Buried ducts without encapsulation should not be installed in moist or marine climates because there is a risk of condensation on the surface of the ductwork. Buried ducts involve placing ductwork as close to the ceiling as practical, either on top of the gypsum board ceiling or over the truss bottom cords, and then burying the ductwork beneath loose-fill insulation. Any loose-fill insulation, such as fiberglass or cellulose, can be used. When more loose-fill insulation is used to boost the duct R value, there is an added benefit of increasing the ceiling assembly R value as well. Buried ducts are categorized into 3 classes based on the distance from the top of the duct to the top of the loose-fill insulation. The classes are partially buried, fully buried, and deeply buried. Partially buried ducts are buried to 3.5 inches below the top of the duct. Fully buried ducts are buried to the top of the duct, and deeply buried ducts are buried with 3.5 inches of loose-fill insulation over the top of the ductwork. Ducts are encapsulated by spraying the ductwork with closed-cell polyurethane spray foam to boost the R value of the duct insulation and reducing air leakage. Although closed-cell spray foam may be applied directly to the exterior of uninsulated ductwork, insulation of ductwork with fiberglass duct wrap prior to encapsulation is a way to increase the duct R value for less cost. Unlike simple buried ducts, where duct sealing prior to burial is a must, encapsulated ducts do not require rigorous air sealing. Ducts should be sealed to reasonable tightness, and then closed-cell spray foam will act as an additional air barrier. In order to be code compliant, the closed-cell spray foam must be approved for exposed attic insulations. In the bed system, ducts are first encapsulated with closed-cell spray foam insulation and then buried under loose-fill insulation. Although initially conceived as a way to apply the buried duct concept to humid climates, where condensation could occur on the outer surface of buried ducts, beds can also be used as a high-performance duct insulation strategy in all climates. Beds have even higher R values than buried ducts and include the air sealing benefits of encapsulated ducts. While there are no significant obstacles to ensuring that buried duct installations are code compliant, installations involving closed-cell spray foam must be carefully considered. In general, the 2009 IRC requires that spray foam insulation applied to the exterior of ductwork covered in sections M1601.3 and M1601.4, and in attics covered in section R316.5.3, meet several requirements. First, the spray foam must have a flame spread index no greater than 50 and a smoke-developed index no greater than 450. Next, attic access is required by section R807.1, which is typically required in low-density residential construction. And finally, the attic is entered only for purposes of repairs or maintenance, meaning no storage or habitation is allowed. In addition, the spray foam must be protected by an ignition barrier, and the spray foam must have a maximum water vapor permeance of 3 perms per inch, which means that open cell spray foam cannot be used. Next, the spray foam must meet the general requirements for use in residential buildings under section R316. Lastly, the IRC allows exposed installation of closed-cell spray foam in attics, but the spray foam must be specifically approved for installation without an ignition barrier under section R316.6. In this case, approval is determined on the basis of specific fire-related test procedures. Note, not all closed-cell spray foam materials meet the requirements of section R316.6. If the spray foam used is not approved for exposed attic installations, encapsulated ducts must also be buried in loose-fill insulation such that the closed-cell spray foam is covered by an ignition barrier. For beds, 1.5 inch of fiberglass, which is considered mineral fiber insulation under ASTM C554-11, meets the minimum requirements for ignition barriers. Beds using a closed-cell spray foam material specifically approved under section R316.6 may be buried under cellulose. All other bed installations require 1.5 inches of fiberglass or mineral wool insulation coverage. The information in this lesson came from research performed as part of the Department of Energy's Building America program. Building America and their online solutions center brings world-class research to your fingertips. The U.S. Department of Energy's Building America research program has been a source of innovations in residential building energy performance, durability, quality, affordability, and comfort for nearly 20 years. You can visit the Energy Department's Building America Solutions Center to learn more about these projects and to find tried and true energy-saving building strategies.